Computing permutations and combinations. These computations are actually from a subject called combinatorics. Um, it's related to counting, but it's not the counting that you're used to. So I'll try to give you some context for these computations. Let's say you have 11 teams in a basketball league, and only 4 of them make it to the playoffs. Well, how many different ways are there to rank those 4 teams that make it to the playoffs? Now remember that the entire league has 11 teams. So if you wanted to count how many different ways that you could rank 4 teams from a sample of 11 teams, then we actually compute a permutation. In other words, order matters, right, when you rank the playoff teams. So when you think or see permutations, you got to remember that order matters. So we're counting the rankings. And how do we compute this? There is a nice formula here. Why don't we write the formula down? And so given n items and you want to permute 4 of them at a time, it is simply going to be n factorial over the parentheses n minus r factorial. And in our case, we're looking at the expression 11 permute 4, which is equal to 11 factorial over 11 minus 4 parentheses factorial. And of course, that's just 7 factorial. So then, factorials, you just count them down to the appropriate common factor, and then we reduce the common factors. And of course, you could put the remaining number in a calculator, and out comes the output, or out comes the expression. Let's do that really quick. 11 times 10, that's of course 110, and then multiply it by 72. And we get 7,920. So lots of different permutations here. When there's a sample of 11 and we permute 4 of them at a time. Let's give this a little bit of context. Let's say you go to a Chinese takeout restaurant and they list 12 things that you could choose from. And they offer a 5-item combo for $6.99. Well, that seems really cheap, but this is hypothetical. So if there's 12 menu items and you want to choose a 5-item combo, does the order matter? Well, in this case, it doesn't, right? So if you ordered, let's say, some fried rice or some chow fun or some General's chicken or some sweet and sour pork, the order of these foods from that list does not matter. You get a choice, or what we say, a combination. So here, if you hear the word combination, the order does not matter. And so we don't want to count all the different orderings, and so this should be less, far less. Well, it's not. If you had to estimate, you're probably going to think it's going to be less than 7,920 because the lists are similar. The first list was 11, this list has 12, but choosing 4 and choosing 5 at a time are quite different as well. There's a formula for this also. We say n choose r. So for n choose r, this formula is n factorial over n minus r in parentheses factorial times it by r factorial. So this looks really, really familiar. It actually has, in fact, all the permutations when you are actually selecting 5 from the list, but then you want to remove all the extra orderings. So this r factorial is saying we want to remove the extra orderings. And the way we do that is we divide by r factorial. So if you look at this carefully, notice that it looks very similar to permutations, but then this takes into account that we want to remove all the extra orderings because order doesn't matter. All right, let's compute our expression. Notice you're not solving anything. You're simply simplifying this expression of 12 choose 5. 12 choose 5 is now 12 factorial over 12 minus 5 in parentheses factorial times it by 5 factorial. Now we reduce things again. 12 times 11 times 10 times 8 times 7 factorial all over 7 factorial. And 5 factorial is 120. So I'm going to go ahead and write that. 5 factorial is 120. And then we could reduce lightly. That's 120. And we're going to reduce the common factor of 7 factorial as well. And then what are we left with? We are left with, does anybody see a mistake? I'll give you a chance to check it there. That should say 9 times 8 times 7 factorial. Let's reduce common factors. So I left the 9 out. We got to put that 9 back in. And now we have 11 times 9 times 8. And how much is that? Well, that should be 792. Let's just double check it. 11 times 9 times 8. It is indeed 792 combinations. So if it helps, you might want to write combinations here. And over here, because order matters, you might want to write permutations here. So that's a good way to remember, are you computing a permutation or are you computing a combination? So why don't I circle this a little bit better? And then over here, let's include the word permutations. So writing the vocabulary always helps. Always write more than less. And of course, that takes more time, so make more time.